This is the hydrocarbon tutorial presented by the SHRTV with reference Cambridge International AS Chemistry by Laurie Ryan and Roger Norris. Hello, hydrocarbon tutorial. So we start with the learning outcome, understand the general reactivity of alkanes, describe the combustion of ethane, the free radical and all that. So just how cracking can use to obtaining more useful alkane and alkane with lower molecular masses. Describe the chemistry of alkenes and all that, the addition, oxidation, polymerization. Describe the mechanism of electrophilic addition of alkenes. Explain the inductive effect of alkenes. So we have the next one. Describe the difficulty of disposal of polyalkenes. Describe the environmental consequences of burning hydrocarbon fuels in vehicles and removal of pollutants in catalytic converters. And lastly, outline the use of infrared spectroscopy in monitoring of air pollution. So we start. So now this is homologous. We need to first start with the homologous group of alkenes. So we need to know that alkenes have a homologous group which is known as the CH3. So a CH3 is going to be added for every CH2 that you have. So let's start. We need to know that a CH3 is going to be added for every CH2. So these are the points for all the alkenes. So now we have said we have already visualized what a homologous series. So now, so what's a homologous series? And we said that it is having the same functional group, and it is going to each molecule differ. The next molecule is going to differ from the previous molecule by a CH2 group, and that CH2 group represents actually a mass of 12 plus 2, which is a mass of 14 grams per mole. So the next element is going to be greater than the preceding. The next element is going to be greater than the previous element by 14 grams. So now these are certain molecules. So this is a three-dimensional view of pentane, and now this is a displaced formula of pentane. So this is a structural formula of pentane, and lastly this is going to be the skeletal formula of pentane. So these are different things to visualize. So now, what are the sources of alkane? So a crude oil is the main source of alkane. So crude oil is found in the trapped layers of rock beneath the surface of the earth. The actual composition of crude oil varies from different oil fields around the world. You need to know that crude oil is a complex mixture of hydrocarbons. You have alkenes, you have cycloalkenes, you have aromatic compounds inside crude oil. Cycloalkenes are saturated hydrocarbons in which here there is a ring consisting of 3 or more carbon atoms. So it's made up of, let's say, a ring of at least 3 or more carbon atoms. You cannot form a ring with 2. So that's why cycloalkane starts with a ring of 3 carbon atoms. So you need to imagine, so these are the things to visualize here. So now this is the displayed formula of hexane, and this is skeletal molecular formula of hexane. But now this is displayed formula of cyclohexane, and this is skeletal formula of cyclohexane. You need to know that the general formula for alkane is given by CnH2n plus 2, and this is why that is another property of a homologous series. A homologous series has a general formula for itself. So now, there are 3 main properties for homologous series. You have number 1, which is you need to know that the homologous series has the same functional group that is going to have same chemical property. The second thing is that the homologous series the next element in the homologous series the next molecule is going to be different from the previous molecule by a CH2 group. The third thing is that the next molecule is going to be different from the previous molecule by a mass of 14 grams. And the last thing is that in the homologous series usually have a general formula. So these are the 4 things involved in the characteristics of homologous series. So now, after having the characteristics, let's see how fractional distillation of crude oil occur, because this fractional distillation is going to be used in the extraction of the different alkanes. So now the question is, this fractional distillation, what is the actual name of this fractional distillation of crude oil? This is actually named as cracking. So what is cracking? Cracking is a conversion, or is a heating. So just say the conversion of a high molecular weight non-volatile high molecular weight non-volatile hydrocarbon to form low molecular weight more volatile hydrocarbon, either by using heat or by using catalytic method. So that is what is called cracking. So there are three main types of cracking. The first type of cracking is going to be a heat cracking. So we have temperature cracking using where you are going to use heat, or that's called thermal cracking. So you are going to hit a heat of 850 to 900 degrees Celsius. You are going to heat it, and when you heat it as such, you are going to form a high you are going to form low molecular weight of alkenes. You have unvaluable you're also going to form unvaluable hydrocarbons, and you can also form alkenes. So low molecular weight alkenes. So these are the things that you're going to form using thermal cracking. The next type of cracking is going to be catalytic cracking. The catalytic cracking, you use aluminum oxide Al2O3 at a temperature of 350 degrees to 450 degrees. See that the temperature here is half the temperature used in thermal cracking, and here in this case it's going to be used in forming more efficient hydrocarbons. The hydrocarbons that are going to be formed here are going to be more efficient and more valuable. So here you have unsaturated and saturated hydrocarbon, which are also going to be formed here. And last one, you have a hydrocracking. Hydrocracking is referred as a cracking process where you put a high pressure on the crude oil, and in this case you use hydrogen. So we put high pressure and hydrogen in the cracking substance. When you do that, you're going to form mostly saturated compounds. So now let's visualize. So this is crude oil which is being passed here. The crude oil enters, and now you have fractional distillation. So as you move up, you have more, the higher the temperature goes, and here down you have lower temperature. So the residues are going to move down. The less valuable part of the crude oil is going to move down, which is going to come down and is going to be pumped away, because this one is not going to be used. And now the steam is going to move up in order to be used in evaporating the cracking substance, the crude oil. So now we have the heavy gases. The heavy gas oil are going to be lost here. Then we are going to have the next one. We have at this position here, we have the reflux heavy gas oil fraction. So the more we are going up, the lighter the gases are becoming, and the lighter the gases are becoming, the more valuable these gases. So this diesel oil we have, diesel oil is going to be more denser compared to super oil inside our total and all that. So diesel oil is something somewhere like this, and then other super oil and kerosene, which are much more valuable and they are used in planes, are much more found up here. We have gasoline, we have kerosene up there. So now let's visualize the reaction of alkane. Before visualizing the reaction of alkanes, we are going to find the solubility of alkane. Alkane are insoluble in water because they are non-polar, that is, they are hydrophilic. So now let's see the reaction of alkanes. We have combustion reaction. That combustion reaction can be used in generating electricity in power station, can be used in generating heat at home and cook our food. So that's what is used inside our gases, so the gas bottles at home. So it's made up of butane and used in cooked food. So we have provide energy needed in industrial processes. We have provide power for ship, aeroplane, train, lorries and buses and cars. All these are alkane in the combustion of alkane. So now we need to know the combustion of alkane. There are two main types of combustion. We have number one, we have complete combustion, and we have incomplete combustion. So let's start with a complete combustion. With a complete combustion, we're going to form carbon dioxide and water. With incomplete combustion, we're going to form carbon monoxide and water. You also form carbon specks. So this is how to balance the equation with carbon dioxide. This is how to balance the equation with carbon monoxide. And now you need to know that what in this combustion there is usually the formation of pollutants, like the pollutants of carbon monoxide, and the other pollutants like nitrogen monoxide, because inside the combustion fuel both nitrogen and oxygen are going to enter the your combustion medium, and then they are going to bind up to produce nitrogen monoxide. But now nitrogen monoxide and carbon monoxide which are being produced are more pollutants. They are going to interfere with your respiration, and they are also going to cause acid rain. These are trees which are being destroyed by acid rains, and this is a condition where you have pollution. It's difficult for you to breathe. So now let's visualize what how to respond to this pollution. So this is why inside new cars, in new technologies of cars, we have catalytic metals inside the burners of the cars. So inside the exhaust inside the exhauster of the cars. So now these burner catalytics are used in the conversion of carbon monoxide and carbon and nitrogen oxide, which are pollutants in air. You have catalysts here. They are going to convert into carbon dioxide and nitrogen and nitrogen in air. These two are less pollutants. So now this is not a pollutant and this is actually a pollutant, but the pollution is not going to compete with your oxygen in air. The problem of carbon dioxide is that it's going to cause greenhouse effect, and greenhouse effect just means that it's a thermal heating. So carbon monoxide in greenhouse effect is just meaning that when you have carbon dioxide, when you have plants, greenhouse effect is a factor that it means that when you have plants in a house, you need to know that one, the plants are going to produce carbon dioxide. So the heat infrared is going to penetrate inside your house, but it is incapable of moving out in the morning because carbon it is unable of moving out because carbon dioxide is preventing it from moving out. So that's the point. So now this carbon dioxide is also acting as a blanket in the atmosphere and thus preventing heat from coming out from the earth's surface. That's why it's going to cause increased heat and temperature in the earth's surface. So now let's also see other reaction of alkanes. Another reaction of alkane is going to be halogenation of alkanes. Halogenation of alkane takes place mostly in presence of light. So we have example hexane plus bromine. If you add hexane plus bromine, in presence of light it's going to react. In no presence of light it's not going to react. So you have no reaction. You see bromine here, you see there is going to be reaction at this time. So the reaction have different processes. We have different parts of the reaction. So step 1 is going to be initiation step, step 2 is going to be propagation step, and step 3 is the termination step. In the initiation step, the light is going to cause chlorine molecule to break into a homolytic fission to produce two chlorine radicals. In the propagation step, the chlorine radical is going to initiate other radicals from the methane molecule or the alkene molecule. So as you can see here, you see that here you have a CH3 that is going to be produced plus HCl, and when the CH3 comes again, produce again another Cl. This is the propagation the propagation. We also have this CH3 bind again with this Cl to produce other molecules, CH3 all that and that. So this is another molecule that is also found in the propagation step. And the termination step, we have the binding of all the unpaired or free radicals. So this is going to bind to produce this, and this is also about to produce this. So these are the termination steps. So this is involved in the reaction of alkanes. So now let's see the other one, alkenes. So now in cases of alkenes, we have now addition reaction. So let's see the reaction of alkenes. But before you see the reaction of alkenes, you need to know that alkenes are homologous series with a double bond, a double bond. So in cases of alkenes, we need to know that what they are homologous series with this double bond, and each molecule separate are different by a CH2 groups. So now let's visualize the alkene molecules. So the reaction of alkene. We have addition reaction of alkene.
we need to know that what the addition reaction of alkene take place in two parts. In this addition reaction, you see the general equation is going to be written as such. But now, when you have an addition of an unsymmetrical molecule, addition reaction of an alkene with an unsymmetrical molecule, you realize that it's going to respect Markov-Nikov rule. And Markov-Nikov rule states that in an addition of an alkene molecule with an unsymmetric molecule, hydrogen is going to bind to the carbon atom with greater number of hydrogen atom, and the other molecule, the other atom, is going to bind to the carbon atom with a lesser number of hydrogen atoms. So I'm going to explain the mechanism of action in cases of binding of a halide, the binding of a hydrogen halide with an alkene, as we're going to see later. So this addition reaction, this is a simple addition reaction in place of nickel catalyst. So you have this ethane molecule that is going to be formed. We also have this addition reaction in case of phosphoric acid or concentrated sulfuric acid at 170 degrees Celsius, and you're going to form this. So these are addition reaction. You're going to form ethanol. So addition reaction now of hydrogen halide. In case of hydrogen halide, you're going to respect Markov-Nikov rule. So you see that these two molecules are going to be formed. Both there is going to be, or this bromine is going to, this hydrogen can bind here, and this bromine can bind here, forming one bromopropane. And this also bromine can bind to this carbon atom here, and hydrogen can bind to this carbon atom here, forming two bromopropane. So these two molecules are capable of being formed in cases of the reaction of this unsymmetric hydrogen halide. But now, the most molecules that are going to be found in the mixture of the products are going to be this molecule 2-bromopropane because of Markov-Nikov rule. So now let's see the mechanism of this reaction to see why most of these molecules are going to be existing in form of 2-bromopropane. So now in the mechanism, we need to know that what you see that this ethene molecule is going to the molecule is going to contain a double bond at this position. So you see that at first point the hydrogen is going to, so this is the mechanism of action where bromine binds with this molecule. Where bromine binds is, you see that two bromine ions are found here. But now let's see the mechanism why this is going to be mostly found in the mixture of the product compared to this one. So the reason is just because you see that when hydrogen first binds to this one, this molecule is an alkyl group. But now you realize that here there is going to be positive. You have initially spoken in introduction of organic chemistry that the primary carbocations, here you are going to have a primary carbocation that is going to be formed when hydrogen is going to bind to this molecule at this second carbon atom. Now when hydrogen binds to this molecule at the third carbon atom, you see that what? You see that you have insert a secondary carbocation that is going to be formed. Since here is a primary carbocation, here is a secondary carbocation, we've initially seen in introduction of organic chemistry that primary carbocations are less stable than secondary carbocations. So it implies that what? More of the secondary carbocations are going to be formed. Since more of the secondary carbocations are going to be formed, most of the molecules are going to exist in this form, and thus they are going to respect Markov-Nikov rule, which states that in the combination of an asymmetric molecule and an alkene molecule, hydrogen is going to bind to the carbon atom having the highest number of hydrogen atom on the double bond. Is it clear? So you can now continue. The next point is going to be the oxidation of alkenes. The oxidation of alkenes can occur in different states. The first point, you have the oxidation here. When you have maximal oxidation, so using concentrated potassium permanganate, Using concentrated process permanganate, you see that a complete oxidation, a full oxidation is going to convert this alkane molecule to produce carbon dioxide and water. Example, when you burn it in air, you have carbon dioxide and water. But now, in case of concentrated manganate, you see that the oxidation is not going to be full. So this is extreme oxidation, this is full oxidation, and this is partial oxidation. So this is partial oxidation and this is full oxidation. So extreme oxidation, you have carbon dioxide and water. Then here you have partial oxidation. You see that it's going to convert to produce aldehyde plus a corresponding aldehyde at this position, and then you have further to produce carboxylic acid, and then you have this conversion from here to here can say you can also produce a ketone. You can also produce a ketone depending on the molecule which is formed, which are present as a reactant. Then we have other addition polymerization. So what is polymerization? Polymerization refers to addition of multiple monomers. So polymerization reaction refers to an addition of multiple monomers in a condensation reaction. That is, there is going to be a loss of a small molecule like water molecule. So now you see that when you add up these molecules together, these molecules are going to add up and they are going to bind each other. So they are going to bind each other, and there is going to be this big molecule that is going to be formed. So this is a polymerization reaction. So you can also have a polymerization reaction in the formation of the peptide bonds, and the formation of peptide bonds is either there is water which is being lost, so with the loss of small molecule. So in this addition polymerization reaction, there is no loss of molecule because of this double bond. So now let's visualize how to find the monomers when you are being given a polymers. In this case you realize that there is multiple repetition of this molecule. That's why this molecule is going to be this, and this is going to be the monomer. So from here we have seen all what should be seen in hydrocarbons. And say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.